This is the interim presentation for the Internal Combustion Engines Lab after week 2, and we are Group A. Our goals in this lab include characterizing, modeling, and optimizing the energy input-output relationship of a 4-stroke IC engine, breaking down the various subsystems and their respective work contributions, such as work done by air, motor, piston, and friction, and to determine the legitimacy of our model and its applications. To begin the lab, the experimental setup is assembled including an IC engine and DC motor connected via belt. Then, by adding different weights onto a lever arm connected to the motor, the torque sensor is calibrated. By running tests on the motor measuring the torque and angular displacement, the motor is characterized with a single rotating mass and 4 rotating masses at various RPMs. Then, a thorough analysis of the data was performed using the work-kinetic energy balance.
So during week 1, we did an energy balance for the motor at constant speed and the motor accelerating from rest, and used that to calculate the moment of inertia for the flywheel. So with the head off of the cylinder, the only two works that are affecting the energy of the motor are the work done by the motor and the work done by friction. We can see here how we calculate that, which is we have work done by the motor is equal to the torque done by the motor integrated over the displacement. Work done by friction is equal to the torque done by friction multiplied by the total displacement. And we can calculate the flywheel moment of inertia when we accelerate from rest based on the final equation below. This week, we're adding a head to the cylinder, and so we have to take into account the work done by the air. During the intake and exhaust phases, the work done will be 0 because the vents will be open. The compression and power phases will result in equal work because we're not injecting any air. And so we're just talking about the amount of air displaced in the cylinder. Because we're assuming adiabatic expansion, we can calculate the final pressure based on the initial pressure and the equation for adiabatic expansion, which is pressure times volume raised to gamma. And for dry air, this gamma is equal to 1.4. Last week, we calculated the moment of inertia of the flywheel with the head removed. We did this by integrating the torque done by the motor over the angular displacement, adding it to the torque done by friction and multiplied by the total displacement, and then dividing that value by the angular velocity of the flywheel. Then multiplying that by 2, we get the moment of inertia of the flywheel.
In order to calibrate the force transducer for the torques on the DC motor, the torque was calculated and plotted as a relation of the input voltage. Then with a linear regression, the general trend was found and quantified above.
Part 2 analysis, we evaluated the efficacy of our model by comparing the theoretical and experimental work due to air during the compression stroke of the IC engine. We experimentally determined the work contributions during the compression stroke to solve for experimental work due to air, and we used the formula to the right to calculate theoretical work due to air. For each of the 6 test cases, we display the angle versus torque and angle versus work plots for 2 4-stroke cycles of the IC engine, where each stroke is separated by 180 degrees of rotation. As expected, the motor work and the compression and power strokes are similar, as well as the intake and exhaust strokes. Our experimental work due to the air was less than half of the theoretical work due to air. For the medium speed 4-mass system, the experimental motor work values for compression and power and intake and exhaust were similarly related to each other. In the compression stroke, a similar discrepancy was reported between the theoretical and experimental work due to error.
Now let's move on to the high RPM 4-mass data. The image in the top left illustrates the segmented strokes. As already demonstrated, the end of the compression stroke is where we expect to see the highest torque value and magnitude. The work for each stroke is shown in the bottom right corner. The image in the top right corner shows the total work in one cycle, and since we're only going to be analyzing the compression stroke to vindicate our theoretical model, the work of the compression stroke will represent the work of the motor. The friction work is the negative value of the intake work. Lastly, the kinetic energy term is calculated by determining the angular speeds at the beginning and end of the compression stroke, as well as the mass moment of inertia. After calculations, the work due to air pressure is negative 9.5 joules. The theoretical value is calculated using the equation below, which is 20.47 joules. Thus, our experimental value is about half of what we expected.
For the low-speed, one-mass system, the total motor work for one cycle was slightly larger than its low-speed, four-mass counterpart. Additionally, an abnormally large exhaust work was reported. As in the previous cases, our experimental work due to error was slightly less than half the theoretical value. For the medium-speed, one-mass system, the total motor work was also slightly higher than the medium-speed, four-mass system. The motor work of the compression and power strokes and exhaust and intake strokes were also very similar. A large angular velocity difference was recorded between the start and end of the cycle, which resulted in an experimental work due to error that was our closest to the theoretical value of all the cases.
Now we would like to talk about the high RPM 1-mass data. We should notice that the data is fluctuating a lot less and that the peaks of max torque are more apparent than with the 4-mass data. The work produced by each stroke is shown in the bottom left corner, and the total work for one cycle is shown in the top right. In this case, our experimental value for work error was about 9 joules away from the theoretical value, which is a better result than the high RPM 4-mass data we found earlier.
In conclusion, we found that the net work done by the air over 4 cycles was approximately 0. No pneumatic injection meant that no work was done on the piston during the power stroke. However, we found that experimentally our data didn't fully line up with that. While our compression stroke and power stroke did seem to follow the trend we would have expected, equal and opposite, the experimental value for both seemed to be about halfway to what we would have expected. This is likely due to a mismatching I-fly component. In the first week of data collection, we found a dataset that seemed incorrect, and so consulting a TA for help, we came up with an alternate solution. However, as this is an exceptionally important factor for the experimental error, and it cascaded down, we found that all of our datasets seem to be about halfway short of what they are supposed to be. If you have any questions, please direct them to the group now or through Piazza. Thank you.